Так, проверяем трансляцию. Всякий случай.
Есть.
Есть?
Да.
То есть поехали тогда.
Да.
Okay, so in the previous lecture we discussed projective and inductive local convex topologies. So let's briefly recall what they are. Suppose I have a vector space X and a family of linear maps from X to locally convex spaces. So X is just an untopologized vector space, and Xi are locally convex spaces. And then we can introduce a topology, a locally convex topology on X as follows. We simply consider the weakest locally convex topology, which makes all the maps phi I continuous. And this is the projective locally convex topology. Explicitly, it can be given by defining family of seminorms as follows. We choose a defining family of seminorms on each of the spaces Xi, and we compose them with the maps phi I. And as a result, we get a family of seminorms on X, and this is precisely the family which generates the projective locally convex topology. So we just compose continuous seminorms on each Xi with phi I.
Is X a projective limit in the category of topological vector spaces?
In general, not, because we don't assume that X is constructed out of the spaces Xi in some explicit way. For example, X can be 0, and Xi are not necessarily 0. But we'll discuss limits today, and the limits, projective limits, are based on projective locally convex topologies. Inductive locally convex topologies are defined as follows. Again, we have an untopologized vector space X. We have many locally convex spaces Xi. And now we have linear maps from the spaces Xi to X. And then we can topologize X as follows. We equip X with the strongest locally convex topology, which makes all the maps phi I continuous. And this is the inductive locally convex topology. This topology can also be given by a defining family of seminorms, which is not surprising because we know that every locally convex topology can be given by a family of seminorms. But in contrast to the case of projective topologies, the defining family of seminorms here is quite inexplicit. We consider all those seminorms P on X such that P composed with phi I is continuous. So we simply describe the property of a seminorm which has to be satisfied, and we consider all seminorms having this property. But we don't have an explicit construction in the general case. In some special cases, we do have an explicit construction. But in the general case, well, that's all we have. Okay, so today we discuss some constructions, some general constructions of locally convex spaces. That is, some methods of constructing new spaces from some initial data, which involve projective and inductive locally convex topologies. And we begin with products. So to begin with, let's recall a general category theoretic definition. Suppose that we have a category A, category, and a family of objects, Xi, a family of objects of A. By definition, the product of this family, product of Xi, is an object, X, of our category, together with a family of morphisms, together with a family of morphisms, say pi I, which act from x to xi, so they are defined for all I, such that the Fourier universal property holds. We require that for every object y in A, and for every family of morphisms phi I from y to xi, which are given for all I in I. So let's now draw a picture. This is x, this is pi I from x to xi, this is y, and this is phi I. So for every such family of morphisms phi from y to xi, there exists a unique morphism, as denoted by phi from y to x, such that this diagram commutes. So this is the general category theoretic definition of a product. And here's standard notation. This object f, object x, if it exists, is denoted like this. Just like the usual Cartesian product of sets. Of course, I don't claim that the product always exists. That depends on the category and on the family of objects. It's quite easy to construct examples of categories where the product doesn't exist in general. Basic example is a case where we deal with the category of sets. If A is the category of sets, then the product of arbitrary family of sets exists. And it is just the usual Cartesian product of sets. And this explains the notation. So the same notation is used for the product in arbitrary category. Pi I, you can only map pi I from x to xi, which appears in the definition, is just the canonical projection of the product onto the I factor. It's the canonical projection. This example, basically this example involves a little exercise. That is to show that the Cartesian product of sets indeed satisfies this universal property. Well, this is very easy. And now by using this example, we can give an equivalent definition of the product. Say, definition of prime. The product of a family of objects xi in our category A is an object of A together with a natural isomorphism. That is an isomorphism of two functors. The first functor is the functor of morphisms from y to this product. And the second one is just the product of confunctors from y to the objects xi. So both of them are functors of the variable y in the category. So again, you see that we are basically in the same situation as at the previous lecture when we defined kernels. So the general principle is that to give a definition of some general category theoretic construction, it is often useful to first to define this construction explicitly in the category of sets, and then to transfer this definition to an arbitrary category by using suitable home functors. So this formula reduces products in an arbitrary category to products of sets. So this is the product of sets, and this is the product in an arbitrary category. But the simple exercise is to show that the definitions are equivalent. Okay, let's now specify the category A. So suppose now that A is the category of locally convex spaces. And so Xi is a family of locally convex spaces. Let's do the following. We first of all take the product of these spaces in the category of sets. In the category of sets. And observe that this is a vector space in a natural way. And we equip this space with the projective locally convex topology. Generated by the projections. Where pi I is just the projection of the product onto the ith factor. So basically the exercise is to show that this is the product of our family in the category of locally convex spaces. So, in summary, we see that an arbitrary family of objects in the category of locally convex spaces has a product.
Ясно. На самом деле это абсолютно то же самое, что топологическое определение.
Yeah, exactly. So we can perform the same construction in the category of all topological spaces, or in the category of all topological vector spaces, if you like, and we get the same space with the same topology. And we, on the one hand, and on the other hand, we get the category theoretic product in the respective category, or in the category of all topological spaces, or in the category of all topological vector spaces, or in the category of all locally convex spaces. So in this case, all these different products taken in different categories are actually the same. Well, a concrete example, if we take an arbitrary set S and the space of all k-valued functions on S, k to the power S, we can naturally identify this space with the product of many copies of the base field. So one copy for any element of the set S. And it's more or less immediate from the definition that the projective locally convex topology here is nothing but the topology of pointwise convergence. Product topology is nothing but the topology of pointwise convergence, which was discussed at the first lecture. Okay, let's now observe that projective locally convex topologies can often be reduced to subspaces of products in the following way. So we start with a vector space X and a family of linear maps phi I from X to locally convex spaces Xi. Family of linear maps to locally convex spaces Xi. So we'll look at the definition of product once again, and we see that this definition gives us a map from X to the product of the spaces Xi. We define phi from X to the product of the spaces Xi. This is just a linear map, so we deal with products in the category of vector spaces. So this is a unique map which satisfies the following condition. The composition of phi with the projection phi I is exactly phi I for all I. So let's now observe that the projective locally convex topology on X generated by the family phi I is the same as the projective locally convex topology generated by the only map phi. Almost by definition, actually the two families of semi-norms which determine this topology and this topology are the same. In particular, if the intersection of the kernels of the maps phi I is trivial, so this means exactly that the kernel phi is trivial. Then X will be X equipped with the projective locally convex topology will be topologically isomorphic to the respective subspace of the product. So we see that an arbitrary, more or less arbitrary projective locally convex topology, that is projective locally convex topology satisfying this condition, can be reduced to a subspace of the product. It's essential to ask about some properties of the of the product. For example, when is it normable, or when is it metrizable? So to answer this question, let's suppose that all the spaces are on zero. So a useful exercise is to show that the product of the spaces xi is normable if all the spaces xi are normable and the set I is finite. And it's also easy to give a metrizability criterion. The second part of the exercise, the product is metrizable even only if all the spaces xi are metrizable and the index set I is at most countable. A hint is here is to use the same trick which was used in the proof of our metrizability criterion 2 weeks ago. Okay, let's now turn to co-products of locally convex spaces. Again, we start with the general category theoretic definition. Suppose that A is a category and xi is a family of objects. The co-product of this family, the co-product of the family xi is an object x of A together with a family of morphisms let's denote them by kappa I from xi to x such that if we write this in the opposite category, then x together with the family will be product. together with this family, kappa I, is the product of this family in the opposite category. So it's useful to write this explicitly. We simply look at the diagram which defines the product, and we reverse the arrows. And what we get is the definition of a coproduct. The product. Okay. We can now look at an equivalent definition of product in terms of home functors. It can also easily be dualized. So an equivalent definition of a coproduct looks as follows. Definition prime, the coproduct of xi is, by the way, I forgot to introduce the standard notation. Standard notation for the coproduct looks like this. So an equivalent definition looks as follows. The coproduct of our family is an object of our category together with the natural isomorphism. Together with a natural isomorphism between the following two home functors. The first one is home from the coproduct to y, and the second one is the product of home functors from xi to y. So both of them are functors of y. And again, a useful exercise, a simple but useful exercise, is to show that the two definitions are equivalent. By the way, I'd like to stress that we define co-products in an arbitrary category in terms of products in the category of sets, not in terms of co-products in the category of sets, but in terms of products in the category of sets. This will be more or less obvious if we look again here and simply reverse the arrows. So the product will still be a product. These two will be interchanged, but this product is still a product. By the way, we have already met such a phenomenon when we defined co-kernels. So co-kernels in an arbitrary category are defined in terms of kernels in the category of sets with a base point. Okay, let's look at some concrete examples of co-products in concrete categories. Examples and simple exercise at the same time. If A is the category of sets, then the coproduct of an arbitrary family is the disjoint union. Disjoint union. And kappa I is just the canonical inclusion of xi to the disjoint union. If we take the category of vector spaces, this is our second example. If A is the category of vector spaces, or for example the category of abelian groups, or the category of modules over an arbitrary ring, then again the coproduct always exists. The coproduct of an arbitrary family is nothing but the direct sum of this family. And again, kappa I is the canonical inclusion of xi into the direct sum. Okay, let's now come back to analysis. Suppose now that A is the category of locally convex spaces, and Xi is a family, object that is a family of locally convex spaces.
У нас получается в этих категориях произведений изоморфные.
Нет, где? В каких?
Вот, в Абелевой группе.
Нет, ни в коем случае.
Сейчас.
What?
Для конечного числа, да, для бесконечного нет.
The difference between, if we work in the category of vector spaces, the difference between a direct sum and product is that product consists of all families of elements, and this one consists of finitely supported families. So it is naturally a subspace of the product. But in general, this is a proper inclusion. The inclusion is they will be the same if I is finite. And if I is infinite, then they are in general they are not the same. If we now take the category of locally convex spaces, we may form the algebraic direct sum, this will be a vector space, and equip it with the inductive locally convex topology generated by the family of all these inclusions. The resulting object is called the locally convex direct sum. The locally convex direct sum of our family Xi is their algebraic direct sum equipped with the inductive locally convex topology. The inductive locally convex topology generated by the family of all canonical inclusions. And now it's now a simple exercise, almost trivial, to show that the locally convex direct sum is nothing but the co-product of our family in the category of locally convex spaces. By the way, if we compare this with the pure algebraic situation, that is with the situation in the category of vector spaces, we see an essential difference here. In the algebraic case, the co-product was a subspace of the product. But this is not the case in the category of locally convex spaces. Here is an exercise. If the index set I is infinite, and all the spaces are non-zero, then the canonical topology, the topology of a locally convex direct sum on our space is strictly stronger. Than the topology induced from the product. So as a vector space, this is obviously a subspace of this, but the topology is different. So from the topological point of view, this is not a subspace of the product. Okay. Well, let's look at a concrete example. Suppose that X is an arbitrary vector space, and let's choose a basis, EI, a basis of X. Of course, not necessarily finite. The interesting case is the case where it is infinite. Then we can identify X with the algebraic direct sum of the respective one-dimensional subspaces, or simply with the algebraic direct sum of many copies of the base field, K. This is an algebraic identification. And now we can equip this with the locally convex direct sum topology. I claim that, this is a little exercise, which is more or less immediate from the definitions, that the topology of locally convex direct sum on X, of course here I mean that each K is equipped with its unique canonical locally convex topology. So the topology of locally convex direct sum is nothing but the strongest locally convex topology. The strongest locally convex topology on X. That is the topology generated by a family of all possible seminorms. Well, basically, this is not an exercise. This is again clear from the definition or from the explicit construction of the direct sum topology. Indeed, all seminorms on the space will be continuous, because in general we consider those seminorms whose restrictions to each of the summands is continuous. But all seminorms on K are of course continuous. Therefore, all seminorms on this space are continuous, and so its topology is nothing but the strongest locally convex topology. Another useful observation, let's come back for a moment to products. When we discussed products, we observed that projective locally convex topologies can often be reduced to subspaces of products. Similarly, it turns out that inductive locally convex topologies can often be reduced to quotients of direct sums. Let's observe that if you have again a vector space and a family of maps, a family of linear maps, phi I from xi to x, a family of linear maps from locally convex spaces xi to x. Then the universal property of coproduct gives us a map phi, we define a map phi, from the direct sum to x, which is uniquely determined by the following condition. The composition of phi with the canonical inclusion kappa I is phi I, for all I. So this property uniquely determines phi. And let's observe that the inductive locally convex topology on X generated by the family phi I is equal to the inductive locally convex topology generated by the only map phi. Again, more or less by the definition of the inductive locally convex topology. So a seminorm of X is continuous if and only if its composition with every phi I is continuous, and this is the same as this is equivalent to say that the composition of the seminorm with the only map phi is continuous. In particular, if the algebraic sum of the ranges of the maps phi I covers X, so if we have this formula, then phi is surjective, phi is onto, and we see that X equipped with the inductive locally convex topology is topologically isomorphic to the respective quotient of the locally convex direct sum. The quotient modulo the kernel of phi. So this observation is quite useful because it often reduces arbitrary inductive locally convex topologies to direct sums and quotients. Again, we have an initial question about normability and about metrizability. So suppose that all the spaces are non-zero, or all I, then I claim, and this is an exercise, that the direct sum is normable, even only if all the spaces xi are normable, and I is finite. And it's also rather easy to give a metrizability criterion. The locally convex direct sum is metrizable, even only if all the spaces xi are metrizable. And I is any ideas, and I is
Most count любой.
and I is finite. This is my favorite exercise because it's very natural to conjecture that I should be countable, but it has to be finite. If it is countable, then the direct sum is not metrizable. Okay. In particular, we see that the strongest locally convex topology on an infinite dimensional space is not metrizable. Is not metrizable. Even if the algebraic dimension is countable, the strongest locally convex topology is not metrizable. Okay. Our next goal is to generalize, to discuss some generalizations of products and coproducts, namely limits and co-limits. So let's start with limits. Suppose now that I is a small category. Small category is a category where the class of all objects is a set. For example, the category of all abelian groups is not small, the category of sets is not small, the category of locally convex spaces is not small, the category of finite dimensional vector spaces is not small, but it is equivalent to a small subcategory consisting of concrete vector spaces, k to the power 2, k to the power 3, and so on. A basic example of a small category to keep in mind, and it's quite useful to keep in mind this example. We start with a closed set, a partially ordered set, and we make it into a category. As follows, I is just a set of objects of this category, and morphisms from I to J are defined as follows. The set of morphisms consists of a single point. It doesn't matter how to denote this point. It consists of a single point if I is less than or equal to J, and the set of morphisms is empty otherwise. And the composition law is defined in the only possible way. So we see that every partially ordered set becomes a small category. And this is very important special case. Okay, now suppose that we have an arbitrary category A, not necessarily small, and covariant functor f from I to A. We have the following auxiliary definition. We define a cone over F is a family of objects. So first of all, it's an object. It's an object X. Together with a family of morphisms. The family of morphisms, let's denote them by phi I, from X to F of I. So they are defined for all objects I of our category, such that for every arrow alpha in our category I, the following diagram commutes. So this is X. Here we have F of I. Here we have F of J. This is phi I. This is phi J. And now the arrow alpha from I to J induces an arrow from here to here. This is F of alpha. So we require this diagram to commute. So this diagram commutes. And now we are ready to define limits. By definition, the limit of F is a cone. Is a cone X together with a family of morphisms phi I over F, such that for any other cone, say Y and psi I over F. So let's now draw a picture. This is X. This is F of I. Here we have morphisms from X to F of I, phi I. This is another cone Y with respective morphisms psi I. So for any other cone Y over F, there exists a unique morphism chi from Y to X. This is chi, such that the diagram commutes for all Y. So in other words, we can define the category of all cones over the same functor F. It's more or less clear how to define morphisms between cones. And from this point of view, the limit becomes the terminal object. The terminal object in the category of all cones. In the category of cones over F. In particular, we see that if the limit exists, then it is unique in obvious way. Again, I don't claim that it exists. Sometimes it doesn't exist. Everything depends on the category and on the family of objects. And on the function. On the functor F. Okay. Equivalently, the same definition can be given as follows. So let's introduce some notation. If I is an object of our category, we can define the so-called the constant functor. The constant functor is denoted by delta I, the delta Y, from I to N. It is constant in the sense that it takes every object, little I, to the same object Y, and it takes every morphism alpha to the identity morphism of Y. The constant functor. And let's now observe that the families of morphisms phi I, which appear in the definition of the cone, are nothing but natural transformations from the respective constant functor delta x to f. And this observation leads to an equivalent definition of limit, the function prime, the limit of f is an object. By the way, again, I forgot to introduce standard notation for the limit. Let's do it now. So the limit of f, if it exists, is denoted simply like this. The limit of f. So an equivalent definition looks as follows. The limit of f is an object of our category together with a natural isomorphism between the set of all morphisms from y to this object and the set of all natural transformations, that is, of morphisms in the category of functors, from delta y to f. So here we take morphisms in the category A, here we take morphisms in the category of functors, from I to A. Okay, let's now look at a concrete category. Well, the most concrete category is the category of sets. Suppose that A is the category of sets. As before, F is a functor from a small category I to the category of sets. We consider the following set, let's denote it simply by X. It consists of those elements in the product xi in the product of the sets f of I, which satisfy the following condition: xj equals f of alpha applied to xi, and this is true for every arrow alpha from I to j in I. So in a sense, X consists of those elements of the product which are compatible in suitable sense. So if you have two elements xi and xj, and if you have at least one arrow from I to j, then we may apply f of alpha to xi, f of alpha to xi, and we should get xj. So these elements in the product are compatible in this sense. I claim that this set is the limit of f. Synthesize. X is the limit of f. And the respective maps phi I from the limit of f to xi, this should be a cone. X should be a cone over the over f. Not to xi, of course, to f of I. To f of I. It's just the usual projection onto the respective factor in the direct product. This is the restriction of the canonical projection. Restriction of the canonical projection. So this is an explicit construction of the limit in the category of sets. And again, similar to the case of products, we may use this construction to give one more equivalent definition of the limit. Definition double prime. The limit of a functor f from I to A is an object of our category. Now, together with a natural isomorphism, between a set of morphisms from Y to the limit of f, and the limit of from functors from Y to xi. Again, we see that an abstract category theoretic definition of a limit in an arbitrary category A can be reduced to limits in the category of sets. So here, in the right-hand side of the formula, we mean the limit in the category of sets. It's the limit in the sense of this example. Okay, so of course, again, I state standard exercise to show that the three definitions are equivalent. This is more or less immediate from the definition, from the definitions, but nevertheless, this has to be verified. Okay. Let's now consider concrete categories. Oh, by the way, before we discuss concrete categories, let's stay for some time in abstract category, and let's observe that products, for example, are special cases of limits. Example 1. Products are limits. More exactly, you have an arbitrary family of objects. A family of objects of A. We can construct the so-called discrete category. Can be viewed as a discrete category.
Таких идиоморфизмов вообще нет между разными?
Only identity morphisms. Discrete category. Morphisms between two objects I and J. So the set is empty if I is not equal to J, and it consists of the identity map if I equals J. Very easy. So we see that a functor from I to A is nothing but an arbitrary family of objects. Indexed by I. Well, indeed, to give a functor, we simply associate an object to any element of I, and that's it. It's just a family of objects. And the limit of this functor is nothing but the product of this family. So we see that product is a special case of a limit. Example 2, this is an example and an exercise at the same time. Show that kernels can also be interpreted as limits. So I leave the details as an exercise for you to define a suitable category I, a suitable small category, and to show that the limit of a functor from this category to A, where A is a category with zero object, is nothing but the kernel of a suitable morphism. Okay. Let's now consider concrete categories. Concrete examples. First of all, let's start with the category of vector spaces. Or we can can take, for example, the category of abelian groups or the category of modules or an arbitrary ring. We take a functor f from a small category I to the category of vector spaces, and we observe that the limit of f taken in the category of sets so the limit of f taken in the category of sets looks like this. It's a subspace, subset in the product. But actually it is a vector subspace. It's a vector subspace of the respective product. And now it's a simple exercise to show that actually this space is the limit of f. Also in the category of vector spaces. So we form the same set as in the category of sets. We equip it with the obvious vector space structure induced from the product, and it becomes the limit of f in the category of vector spaces. Okay, and now let's look at the category of locally convex spaces. Here we have a functor f now to the category of locally convex spaces. And let's equip the limit of f taken in the category of vector spaces with the projective locally convex topology. Generated by the family of projections. To f of I over all I. Or equivalently, as we have already observed, this topology is identical to the subspace topology of the product, with the topology induced from the product. A simple exercise is to show that this space, the limit of f with this topology is nothing but the limit of f in the category of locally convex spaces. The resulting space is the limit of f in the category of locally convex spaces. So we see that every functor f from a small category to the category of locally convex spaces has a limit. Let's now look at an important special case of this construction. Suppose that I is a partially ordered set, and it's convenient to assume that I is directed. Let's recall that I is directed if for every pair of elements I and j, there is another element k such that k dominates both I and j. And if A is now an arbitrary category, then by definition, an inverse system or a projective system in A is an arbitrary covariant functor f from the category opposite to I to A. It's essential that here we replace I by the opposite category. Or equivalently, we consider a countervariant functor from I to A. So explicitly a projective system is a family of objects xi indexed by elements together with a family of morphisms phi ij which act from xj to xi, and they are defined whenever I is less than or equal to j. That is, whenever we have at least whenever we have a morphism from I to j in our category. So all this data is in our system, and of course these morphisms should be compatible in the sense that if I is less than or equal to j and j is less than or equal to k, then phi ik should be equal to phi jk. And of course, phi ii is the identity map. So this is an explicit form of a projective system in an arbitrary category. In the case of projective systems, the limit of every such functor is called the inverse limit or the projective limit of this functor. The limit of f, which acts from I opposite to A, is often called the inverse limit or the projective limit. And the standard notation looks like this. We equip the limit sign with an arrow from the right to the left, or simply forget about f and write the limit of the family xi. It's a slight abuse of notation here, because of course this object depends not only on the family of objects, but also on the family of these connecting maps. By the way, the maps phi ij are called connecting maps, the connecting maps of our family, of our system. But usually this standard abuse of notation doesn't lead to any problems. So we write the limit of xi and assume that phi ij are also given. So the explicit picture for the limit, for the projective limit, now looks as follows. So these are our objects xi and j, xj. Here we have the maps phi ij, which act from xj to xi, where I is less than or equal to j. So the limit of xi should be common. So we have maps from here to here. And for an arbitrary cone, y, that is for an arbitrary object, and the family of morphisms from y to r objects, which are compatible to each other in the sense that the diagram commutes, there exists a unique morphism from here to here, such that the whole picture is a commutative diagram. So this universal property explicitly describes the projective limit. Well, it's time to finish, but I feel that I must give at least one or two examples, because otherwise the whole construction looks too abstract. So just a couple of examples, and some more interesting examples will be given at the next lecture. Example 1. Suppose that X is a locally convex space, and suppose we have a chain of subspaces, a decreasing chain of subspaces. This can be viewed as a projective system. This is a projective system over the natural numbers, indexed by the natural numbers. So for every, if I is less than or equal to j, then we have just the inclusion map from xj to xi. Connecting maps are inclusions. I claim that the limit, projective limit of this sequence is nothing but the intersection for the obvious reason that they both satisfy the same universal property to give a compatible family of maps from some locally convex space Y to this chain is the same thing as to give an arbitrary map from this space Y to the intersection. Example 2. Let's consider the following a projective system over natural numbers. The arrows are just projections. So the first arrow projects x1, x2 to x1. The second arrow projects x1, x2, and x3 to x1, x2, and so on. So this is a projective system again over the natural numbers. And I claim that the projective limit of this system is nothing but the space of all sequences equipped with the product topology. This is an exercise for you. The simplest way of doing this exercise is to show that this satisfy the same universal property. Okay, so that's all for today. And in the next lecture, we first of all we discuss some more interesting examples of projective limits. So my general point is that projective limits exist in the category of in the theory of topological vector spaces everywhere. They are everywhere. When we take any sufficiently good locally convex space, and it can very often be represented as a projective limit of some spaces which are often, for example, they are often bound spaces. And next we discuss dual construction, we discuss co-limits, and again we will see that there are many concrete locally convex spaces which can be represented as spherical co-limits.